Welcome back. Last time we started looking at this Zosi Wi-Fi CCTV camera. What we found was it was a high silicon based device, so we've got the high silicon SoC here. It has SPI flash on the back of it and it's got a USB Wi-Fi board, Realtek chipset. I've simplified the device, I've pulled the bits off that we don't need. I've left the Wi-Fi board on there because I don't know what would happen if it wasn't on there. One of the things that we noticed on this, the thing that was of most interest really, in terms of an attacker, is what looks like a serial port down at the bottom here. Why do I think it's a serial port? Well, it says GTR, ground, transmit, receive. 3 and 4 pin headers like this are so commonly serial ports, and that might allow us access to the operating system. It might give us access to a login prompt for the operating system, or possibly the U-boot console on this device, which would allow us to get hold of the firmware. So we want to work out how this pairs with the DVR, and the firmware is kind of key there. Now, the first thing when we're connecting to a serial port that we need to do is we need to make sure that ground is in fact ground. We need to make sure that we're connecting things the right way around. So we've got that G pin down the bottom. I'm just going to connect my multimeter there. Now, the first thing when you're using a multimeter is make sure it's working. Make sure the continuity tester is actually making noise. So I'm just going to connect the probes together. You can hear that beeping. I know the multimeter's working. Now on a board like this, we need to find an obvious ground to check that it's connected to there. On something like this, you've got something called a ground pour or a ground fill. The bits, the PCB that aren't doing anything are just filled with ground because it reduces noise. And you can see on each corner we've got this big expanse of copper. It's almost certainly ground. You can see it's connected through. So you can see all of these big copper bits are connected to there. It's almost certainly ground. Another good place are the big solder pads at the end of connectors. These are used for mechanical strengthening of those connectors. They're nearly always grounded as well. Right, so I'm confident now that that G is in fact ground. It is a ground. So now we can safely connect a serial adapter to it. So what are we going to use to do that? Well, we're going to use a USB serial adapter. This is one of those. It's a CP2102, I think. I can't see the markings on it. It's just a USB serial adapter. It converts USB through to serial. They're dirt cheap, about £1. I like using these because if I break one of them, it's £1 loss, whereas more expensive ones like FTDI chips, they cost, £8, £10. These are cheap and they're reliable. They work. They do the job. We're going to connect it through to a USB hub. I really like these switched Sabrent hubs. You find yourself power cycling USB devices an awful lot when you're using virtual machines and USB devices, and that switch is just so much easier than plugging and replugging the device. This one's USB 3, which is quite good. So yeah, it's a nice little device. So I'm going to plug the USB adapter in there, keep the power off at the moment. The device isn't powered either. And what I'm going to do is I am going to connect the serial adapter through to the board. Now we need to flip, transmit and receive. Okay, so first off on here we've got receive, which needs to go to transmit. So transmit is the brown one here. So I'm going to take that and I'm going to hook it onto the board. So these little test clips are great. It means you don't have to solder. The next one I want to go receive on the serial adapter through to transmit on the device. So again, let's get that in there. Remember, they're powered off. There's no real chance of damaging anything. And then, of course, we need ground. You always need a ground. Make sure you've got that ground common between the two devices because we're working on voltages, potential differences between the two. Oh, so I've just popped that off, moving it. So there's one disadvantage with these test clips. They do sometimes fall off. You do have to be a little bit careful, but I don't have a soldering iron with me, and this is the easiest way of doing things. Right, so we now have the device connected up. Physically connected up, and we now need to interact with that serial adapter. So I'm going to jump through to my virtual machine. I'm going to power up the USB serial adapter. So now that's connected, and what we're going to do is we're going to jump through to the virtual machine and I'm going to run dmessage to check that it's actually turned up. So we've got a CP210X converter now attached to TTY USB 0. Depending on the type of adapter you use, it might be TTY USB 0, it might be TTY ACM 0. Doesn't really matter. We're then going to use Minicom. Minicom-D, that means device/dev TTY USB 0. And we're now in Minicom. Massive assumption here. I think this is going to be running at 115/200 bits per second, 8 bits, no parity, 1 stop bit. It's almost a given with these high silicon things. They're so common. So now I'm going to power the device up. Right, so I power it up, and there we've got U-boot. So we saw U-boot there, and now we've got stuff flying past. These high silicon things are really chatty. They throw stuff out to the console, which does make them a little bit hard to follow. So I'm just trying to keep up with what's going on here. Oh, okay, login prompt. I saw a login prompt. Yeah, okay, so if I hit enter, you can see there we've got none login. We're struggling to see it with the stuff that's being spewed out to the console. But let's try blank blank. Login incorrect, root blank. Login incorrect, root. You'll notice stuff's flying past on the screen. Your typing isn't impacted by that. It just makes it awkward to see what you're doing. Login incorrect, root 1 2 3 4 5 6. Incorrect. Okay, so we've got a bit of a problem here. So it's got a Linux login through the serial console. It's quite awkward brute forcing these because you need to work out if you succeeded or not. And when you've got this stuff coming through the console, it can be quite hard working out. It's also slow to brute force this way. Okay, right, next steps. I think we need to take a look at the U-boot console and see what we can do from that perspective. So what I'm going to do is I'm going to power cycle the device, and I'd imagine we're going to get a U-boot console pop up right at the beginning. I'm probably going to have to press a key to get into it, and I'm going to do that quite quickly. So let's go for power cycle. Yeah, hit any key to stop auto boot. Okay, now we're in the U-boot console. High Silicon, it's kind of like a custom version of U-boot that they use. First thing we're going to do is type help. Right. Okay. So yeah, we have TFTP. TFTP is great because it means we can transfer the firmware out over a network connection, and it's really fast. We've got SF to work with the flash, the SPI flash, which is good. So it's not memory map flash. You have to interact with it kind of like in a separate memory addressing space. And we've got printenv, so we can see what the devices are actually doing as it boots. Let's start with printenv. Right, okay. Looking at this. Boot args. These are the arguments passed through to the kernel from the bootloader. You can quite often root devices by modifying these. That's probably something for discussing another time. It's a bit backwards and forwards, trying to work out what works there. The next one, boot command. This is what U-boot runs to actually boot the device. So let's break down what's going on there. SF probe 0. So first off, that's probing the SPI bus for flash chips. That makes sense. SF read. Okay, so this chunk in the middle here. So what this is doing is it's reading from address 40,000 in the SPI flash. It's reading this many bytes from the SPI flash, and it's reading it into this address. This address here is RAM on the high silicon chips. So it's copying the SPI flash into RAM, which is expected, and then it's doing boot. It's booting from that address. So what's happening here is it's copying, or what I think is happening here is copying the SPI flash, not the first bit of it, it's skipping the start of it into RAM, and then it's booting. The start of it will be U-boot, the thing we're looking at the moment, so it doesn't need to copy it. We've then got the IP address of the device and the server IP. These are just the addresses used when you're using TFTP. So what we can do is we should be able to copy the firmware out over TFTP. So first things first, let's check this actually works. SF probe 0. Okay, cool. Right, 16 megabytes of flash. So it's found the flash device, which is good. Now we need to do SF read. Kind of the same as the boot command. We need to copy it into the same address in RAM. Oh, whoops. So we copy it into the same address in RAM. We need to start from the beginning. We don't want to skip that first bit. Something interesting might be there. And then we want the whole 16 megabytes. which is 100 4 zeros. Okay, so that's copied it. It took a little bit of time. It does take a little bit of time because it's having to copy data. So it's copied that across. So now we need to set up the network connection so that we are 192.168.2.125 and we can TFTP that data. Okay, so we should be able to do that. Right. Let's come through here. I'm going to use NM Connection Editor to set up a device. Now, what I'm going to use is a USB Wi-Fi adapter. It's one of these. These are great. Rather than using the network adapter that's in your proper machine, you pass USB through to the virtual machine. It just avoids so many of the complexities with networking. So I'm going to plug that in, turn it on, and I'm going to go back and change the settings here. So it should probably, yeah, it's on DHCP, which is kind of standard. I'm going to change it to manual. Add an address, 192.168. Is it 2.125? Oh, whoops, 2.125. Sorry, it's Friday evening. I've had a couple of beers. 2.125. Net mask will be 24. We don't really care. Don't need a gateway. Press save. Okay. So now we have that set with a manual IP address. We then need to connect the network cable. So that's pretty easy to do. So we just take the network cable and connect it through to there. I can see there's activity LEDs, which is good. So the device is now powered. Just run ifconfig. Yep, so we can see there 192.168.2.125, the interface is up. So we're good, we're connected, at least on the lowest level of the Ethernet interface. So now we need to run the TFTP command to copy it across. I've already got it set up on this machine because this is something I do quite a lot. So it's TFTP, the address you want to copy from, the name of the file. Now, weird thing about TFTP is you can't actually create files. You can overwrite them, but this means you have to create the file on the server first. So this firmware.bin is what I always call it, just because it's an easy way of doing it. I've created that file on the machine. Then you need to tell it how much you need to copy. So that's a 100 4 zeros again. Okay, so yep. Okay, set up that Ethernet control. Okay, cool. It's copying. So this is successfully transferring that firmware.bin through to the laptop, the virtual machine here. Right, okay, so we now need to get this across. I have completely forgotten where it stores the files. It changes between different distributions. Okay, hold on a sec. This is properly lazy. Let's see where it stores those files. var lib tftp boot. Obviously, that's where it is. var lib tftp boot and firmware.bin. Copy it across to here. Wow, forgot the command there. Special, properly special. You can see what happens when I'm recording stuff. Okay, I've copied it here. I want to make sure it's owned by me rather than someone else. Okay, cool. So that's owned. So now we've got firmware.bin, and it is 16 megabytes in size, which is as expected. So we've got a 16 meg firmware binary. File says it's data. That just means it doesn't know what it is, which is kind of what we'd expect. So let's run binwalk on it. -e extract. So I'm just going for extraction straight away. Okay, right. So there you go. We've got from 40,000. We've got a image header. That was what we expect. We saw that 40,000 in the offset that was being copied initially. After the image header, 40 later, we've got the Linux kernel. Again, that makes sense. A GIFs2 file system. Okay, I'm fairly certain what's going to now happen is it's going to find lots of zlib, it's going to find lots of GIFs2, what's happened here is Binwalk is repeatedly finding signatures for various file systems, and we're going to end up with a massive directory structure of stuff that maybe doesn't really make sense. But let's just keep on going with it. I don't know how long this is going to take. It could take ages. It could be really quick. So this is quite common. Binwalk isn't a silver bullet. It doesn't work all of the time. Realistically, it might be better for me to work out how big the kernel is, trim that off the top, make the rest into a GIFs file system and mount that directly. I think, however, that wouldn't work. So yeah, it's keeping on going. You can see it's running all the way through there. More GIFs, more zlib. I think this is going to continue for quite a while. I'll cut this out. I'm sure I'll cut this out. I'll definitely cut this out. I'm cutting this out. Don't you think dogs have got really, really small during lockdown? I think dogs have shrunk or something. I've just seen so many tiny dogs. It's really weird. And we're done. We're done. We're finished. Okay. So Binwalk extracts to underscore name of the file. And let's just check, see if we've got anything. So just find out. Yeah, okay, we've got lots. We have a lot of stuff there. So you can see we've got various file systems. Oh, it's a bit of a mess. Right. We want to explore this. So the first thing we want to do is see is the shadow password file, because that's where might be where the hash is stored. Okay, no shadow. A lot of these embedded devices don't use a shadow. That's maybe because they only have root, and there's no point in having a shadow password file if the only user's root. So, okay, we've got lots of password files. Lots of password files. Right, let's see what's in those. Oh, what's going on there? Yeah, okay. So we've got a bit of an issue here that loads of this stuff's like malformed. Let's do grep recursive root colon, because that would be in the password file. Okay, so loads of those little files it's extracted have got them in. It's kind of it keeps on finding the same files. This is relatively common. I shouldn't have been lazy here. I probably should have mounted it. Okay, this looks better. This looks better. Right, so we've got things that look like normal password files. So we've got a password file and we've got a password dash file. So it's like an actual file and a backup of it. Right, so let's see what's going on with that one. Okay, so we've got a conventional password file there with one user root and an MD5 password hash. And what's this password dash one? But this is like the legacy one, so that looks like a descrypt hash. Oh, whoops, messed that up. Yeah, okay, so that's using a descrypt hash. That one there. Okay, let's copy that across. So it looks like we have a password hash. Actually, no, I'm not gonna try brute forcing this. Let's go for the really obvious one. Let's Google it. So these are a device that is for sale in lots of places. Oh, great. So we've got two RSSing things, and then we've got a forum in Russian. Interesting. So it doesn't look like too many people have mentioned it. So, oh, is this my device? Not quite. But it is a Zosi. Okay, let's search for that hash there. So how have they gained access? There's a shell here. Interesting. enter the dead camera via U-boot via UART, get the root password hash, find the password by the hash, read the flash drive via USB TTL and find the password there. It did not work. Go to the working chamber via telnet with the password and download the dump. Fill the dump into the broken camera. I think I might need to read that offline to work out what's going on. So we've got a password hash. We could try and crack that. I kind of get the impression from the lack of results on Google that no one's done that. The other thing we might want to do is see if we can find SSID in there. And we see it a couple of times. So we're seeing SSID and kind of like a fixed string. Let's scroll through. Again, like if I don't have to root this, I might not be so interested. I might just want to work out what the Wi-Fi password and SSID is. Is it derivative? Is it fixed? What's going on with it? Oh man. So let's go up through there and see what the interesting things are. hostapd.conf. So that looks like IPC underscore a MAC address. Okay. So I've seen Wi-Fi networks with that name. Let's go into that directory. Let's look at hostapd.conf. Okay. SSID IPC underscore MAC address, and then the WPA passphrase is 1, 2, 3, 4, 5, 6, 7, 8. Now, odds on that's hard coded. I really doubt that I've ended up with one camera that's got the serial number or Wi-Fi password of 1, 2, 3, 4, 5, 6, 7, 8 just by pure chance. What was the other one? It was WPA-psk.conf. Let's have a look at that. SSID, MVR, blah, 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 blah. Key management, PSK 1, 2, 3, 4, 5, 6, 7, 8. I'm fairly certain now that these cameras are just connecting to anything with an SSID like that, specifically that, and then logging in with the password 1, 2, 3, 4, 5, 6, 7, 8. Which isn't great, really, in the general scheme of things. I wonder if there's been some kind of handshake that happened before this. The thing is, though, I haven't powered this camera up with the DVR. The DVR is here, I've powered it up, but this camera and the two of them have never been powered up at the same time. So this is interesting. We've got the firmware, and we've learnt something about how this works. Now, I think the next step is gaining root access to this camera. The ways I can think of doing that are I could take this firmware we've extracted, repack it with another root password hash and then gain access. That might be a bit awkward. People tweak file systems, they change them, and it gets a bit difficult. The other thing that we could do is we could try modifying the boot arguments to the kernel. So quite often that will have /bin/init.sh or something like that. It will run something when it starts, but we can change it so it just runs bash and we're straight in. The other perspective we could come at it from is the network interface once it's actually booted. We're looking at the U-boot console network interface. We've not looked at the operating system yet. But I think we've learned something interesting there. I hope you enjoyed that. This was pretty ad hoc. I've had 3 beers, and things don't always go to plan. I was hoping we'd be straight in as root on that serial console, but we've certainly learned something about this device. And I will be doing another one of these videos probably in a few days. So like and subscribe, and then you'll get notified for the next one. Thank you for watching. Bye.